Everyone. I am absolutely thrilled you're tuning in because today we're diving into a literal microscopic superpower. We're going to explore a technology that lets us look at materials on a scale so incredibly small, it honestly feels a bit like science fiction. But I assure you it is very real and it is completely reshaping how we understand the physical world around us. Let's get right into it.
Picture this for a second. If you've got a massive chunk of rock in front of you, figuring out what it's made of is, well, pretty straightforward. But how do we figure out the exact chemical recipe of a microscopic speck of dust? Or what about a tiny nanometer-scale defect on a computer microchip? When things get that incredibly small, traditional chemistry just doesn't cut it anymore. We need something infinitely more precise. And that sets up the exact problem this incredible technology was designed to solve. So, here is our game plan for today. We're going to start by defining this microscopic superpower. Then we'll break down how the machine actually works, zoom right into the interaction volume, decode the data it spits out, explore elemental maps, and finally wrap up with why this technology is an absolute game changer.
Okay, Section 1, the microscopic superpower, morphology versus composition.
It's really fascinating to contrast these two fundamental ways of analyzing a sample. You see, morphology gives us those stunning, high-resolution physical shapes using the FESEM. It shows us exactly what the sample looks like. But, looks aren't everything, right? Composition is where EDS steps in. It gives us the actual underlying chemical recipe. When you marry these two together, you get an unmatched analytical superpower.
Moving right along to Section 2, how EDS actually works, the top-down journey. Let's trace the path right inside the instrument itself. We start up at the very top. The electron gun fires a beam straight down through a series of condenser lenses, an aperture, and an objective lens. Basically, these magnetic lenses act to perfectly focus that electron beam until it strikes our sample sitting all the way at the bottom. And tucked right in next to that sample, pointing directly at the impact zone, is our EDS detector, specifically a Silicon Drift Detector. It just sits there, waiting to catch the specific signals bouncing off the sample.
So it basically boils down to this really elegant four-step journey. The electron gun fires, the lenses focus the beam into a super tight spot, the beam hits the sample, and finally, X-rays bounce off and are caught by the Silicon Drift Detector. You can kind of think of this highly focused electron beam as a targeted spotlight, but instead of just illuminating the surface, it forces the sample to literally reveal its deepest elemental secrets. Now for Section 3, inside the interaction volume, where the magic happens. When that high-energy electron beam smacks into the sample surface, it doesn't just bounce right off. It actually digs in, creating what we call the interaction volume. It forms this really fascinating teardrop-shaped zone just beneath the surface. And the depth of this zone is tiny. We're talking anywhere from roughly 10 nanometers to maybe a few micrometers deep. This depth is absolutely vital because it dictates exactly where our data is coming from, and it actually shifts depending on the accelerating voltage of the beam and how dense the material is. Inside that little teardrop, it is absolute chaos. The primary electrons from the beam interact with the atoms of the sample, and they scatter three main things out into the vacuum chamber: secondary electrons, backscattered electrons, and characteristic X-rays. Now, while the electrons are what give us our high-resolution FESEM images, for our chemical recipe, we are exclusively focused on those characteristic X-rays. The EDS detector collects those specific X-rays and seamlessly converts them into an electrical signal.
Which brings us to Section 4, decoding the EDS data, spectra, and numbers.
The software takes those electrical signals and spits out an EDS spectrum. This is a graph plotting counts on the vertical axis against energy in kiloelectron volts on the horizontal axis. Notice those distinct, sharp spikes? Those are the ultimate atomic fingerprints. Every single element on the periodic table emits X-rays at incredibly specific, known energy levels. So when we see a peak hit a certain energy level, there is no guessing. It absolutely proves the presence of a specific element, whether that's carbon, oxygen, silicon, or even gold. But wait. It gets better. This spectrum isn't just a list of ingredients. If you look closely at the size of those peaks, the peak height, or more accurately, the total area underneath that peak, is a visual metric that is directly proportional to the concentration of that element. Simply put, we can tell not just what element is in the sample, but exactly how much of it is sitting right there. A massive peak means a huge concentration. A tiny little blip means just a trace amount. And then, boom,
The software takes those visual peaks and automatically translates them into hard quantitative numbers. We get a complete breakdown of the elements: carbon, oxygen, aluminum, silicon, zinc, gold. For every single one, we get the exact weight percentage and atomic percentage. Literally in seconds, we've gone from an unknown microscopic spec to a perfectly precise, mathematically exact chemical recipe totaling exactly 100%. It's wildly powerful when you think about it.
Let's look at Section 5, Painting with Elemental Maps, Visualizing Spatial Distribution.
Analyzing a single point is cool and all, but what if you have a really complex sample with different materials all mixed together? That's where elemental maps come into play. These are color overlays generated by scanning that electron beam across a wider area of the sample. So instead of just staring at raw numbers in a spreadsheet, this feature lets us visually map out exactly where specific elements are physically clustered on the surface. The software basically assigns a vibrant color to each detected element. Say, aluminum is shown in red, silicon in green, oxygen in dark blue, zinc in light blue, and gold in yellow. When you view these maps side by side or combine them into a gorgeous final overlay view, it instantly highlights the chemical structure of your microscopic sample. You can literally see a grain of gold sitting right next to a clump of silicon. It takes all that abstract data and turns it into a highly intuitive, incredibly colorful heat map.
Section 6. Why this technology matters. Key benefits.
Why is this such a big deal for industries around the world? Well, it boils down to 5 main benefits. First, rapid elemental identification, finding elements in incomprehensibly tiny spots. Second, quantitative analysis, giving us precise, reliable measurements. Third, elemental mapping, providing that immediate visual spatial distribution. Fourth, high spatial resolution. Thanks to that highly focused electron beam, we get incredibly localized data. And fifth, maybe the most crucial one, it is non-destructive analysis. The electron beam does not destroy the sample. You can analyze a priceless geological artifact or a super delicate semiconductor, and it remains completely intact.
Because of this unique combo of capabilities, EDS inside of FESEM really is the ultimate microscopic detective tool. It is an absolute necessity in material science for developing new alloys. It's the backbone of quality control in nanotechnology and semiconductor manufacturing. Geologists use it to understand mineral formation. Metallurgists use it to diagnose metal fatigue, and forensic scientists absolutely rely on it to analyze gunshot residue or microscopic paint chips at crime scenes. The applications are, for sure, virtually limitless.
So, to wrap this all up, just remember this simple equation. EDS plus FESEM equals morphology, what a sample physically looks like, plus composition, what it is fundamentally made of. By mastering this instrument, we aren't just looking at the microscopic world, we are truly, deeply understanding it. So I'll leave you with this thought. If you could place absolutely anything inside this vacuum chamber and reveal its deepest elemental secrets, what hidden microscopic world would you want to explore first? Think about it. Thanks for joining me on this explainer, and keep learning.